In this video, I shall present the concept of heat capacity. I shall review the various definitions of heat capacity and consider the ramifications of carrying out processes at constant volume and constant pressure. When a substance is heated, its temperature rises. The magnitude of the temperature change depends on the object's heat capacity. When an object is heated, its temperature may rise rapidly, in which case it has a low heat capacity, or it may rise slowly, in which case it has a high heat capacity. Professional chefs invariably have a side towel tucked into the waistband of their apron to enable them to pick up metal-handled pans full of boiling water, as metals get hot very quickly. Observe these two objects being heated at similar rates. The object on the left heats up quickly and therefore has low heat capacity. The object on the right heats up more slowly and has high heat capacity. Heat capacity is defined as the energy required to raise the temperature of an object by 1 degree centigrade or 1 Kelvin, and it is measured in joules per Kelvin. Heat capacity C is equal to the heat energy supplied to an object, Q, divided by its corresponding change in temperature, delta T. This important equation is given as equation 6. Heat capacity is an extensive property. That is to say, its value is dependent on the amount of substance under consideration. For example, it will take significantly less heat to raise the temperature of 1 drop of water by 1 degree than it will to raise the temperature of an entire swimming pool by 1 degree. The swimming pool will therefore have a far higher heat capacity value than the droplet of water, even though both are made of the same substance. There are two ways to make heat capacity values intensive, i.e. independent of amount of substance. Heat capacity divided by mass of substance is termed specific heat capacity, symbol CS, units, joules per Kelvin per kilogram. Alternatively, heat capacity divided by amount of substance is termed molar heat capacity, symbol Cm, units, joules per Kelvin per mole. Both specific heat capacity and molar heat capacity are intensive quantities. The following slide will showcase a range of different materials and show their specific heat capacities in joules per Kelvin per kilogram. From lowest through to highest, the materials are gold, mercury, copper, bone, diamond, graphite and sulfur, sugar, paper, plastic, wood and rubber. Notice how the metallic substances have low heat capacity. This is in part due to their density, but also because metals absorb heat rapidly and heat up rapidly. Materials that we would consider insulators, such as paper, plastic, wood and rubber, have far higher heat capacities. Isochoric heat capacity, CV, is heat capacity recorded at constant volume and is defined as the heat supplied at constant volume, QV, divided by the change in temperature, delta T. However, in lecture 4, covering the first law of thermodynamics, we proved that QV is equal to the change in internal energy, delta U, and thus the isochoric heat capacity is the change in internal energy divided by the change in temperature. This result is quoted as equation 7. Isobaric heat capacity, CP, is heat capacity recorded at constant pressure and is defined as the heat supplied at constant pressure, QP, divided by the change in temperature, delta T. However, Again, in lecture 4, covering the first law of thermodynamics, we proved that Qp is equal to the change in enthalpy, delta H, and thus the isobaric heat capacity is the change in enthalpy divided by the change in temperature. This result is quoted as equation 8. Thus, the isochoric and isobaric heat capacities represent the slopes of the graphs of internal energy U and enthalpy H against temperature respectively. Now let's consider the relationship between the molar isobaric and isochoric heat capacities for an ideal gas. By definition, H, enthalpy, is equal to U plus PV. Thus, for 1 mole of substance, molar enthalpy is equal to molar internal energy plus pressure multiplied by the molar volume. For an ideal gas, PV equals nRT, and thus for 1 mole of gas, PV molar equals RT. If we now replace PV molar with RT in the second equation on the slide, we get that the molar enthalpy is equal to the molar internal energy plus RT. At 298 Kelvin, RT is approximately 2.5 kilojoules per mole, and this is not negligible for a gas. If we now assume a change of temperature, delta T, then the molar enthalpy and molar internal energy will change according to delta H molar equals delta U molar plus R delta T. Dividing through by the change of temperature, delta T, yields delta H molar over delta T equals delta U molar over delta T plus R. But from equations 7 and 8, this gives Cp molar equals Cv molar plus R, where R is 8.314 joules per Kelvin per mole. This equation is given as equation 9. Thus, the isobaric molar heat capacity of an ideal gas is greater than its isochoric molar heat capacity by 8.314 joules per Kelvin per mole. In practice, values may differ from this owing to the deviation from ideality of real-world gases. In the next lecture, we will begin to look at the second law of thermodynamics and introduce the concept of entropy.